Okay, so this is chapter 3.23.8. It's required for your CA week 9 physics. All about magnets. It's so easy. This stuff, fact theories, they're just stuff, yani, they're required, they're habal, yani, okay? Please read over them in the notes. You should know that a fact is something that actually exists. Okay, a fact can be observed or measured and it's actually supported by evidence. This is important. A fact is always supported by clear evidence. A theory doesn't have evidence. It's an explanation which correlates and interprets facts. La 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 la. And a theory is a group of general propositions used as principles of explanation for a class of phenomena, like Einstein's theory of relativity. It's just a theory, but it's a theory that talks about energy and how our Earth exists as a whole. But it's not proven. Okay, a theory is an analytic structure designed to say, okay, whatever, whatever, whatever. This is the important part. A generalization can never be proven true. It can only be supported by experiments. Okay, a generalization is falsified when one experiment contradicts it. Okay, the famous example is the um, the apple example. A guy, he had 15 green apples and he was like, oh shit, green apples all taste sour. Okay, so he kept on eating them, and then his 15th green apple, it actually tasted sweet. So that means it falsifies his generalization that green apples are sour. Okay, now let's actually start with magnetism. Magnetism is the name given to a class, okay, which exhibits interactions similar to those observed by magnets. Okay, the interactions are modeled by what forces? Magnetic forces. He, yeah, magnetic forces work with electric forces is important to be considered as electromagnetic forces. Okay, which is one of the four fundamental forces. Okay, you should know this. This is probably going to be a multiple choice. Magnetic forces are most strongly observed in ferromagnetic materials. This is important as well. Ferromagnetic materials are those materials that exhibit strong magnetic properties. Okay, they include cobalt, nickel, steel, and ceramics. Okay, these are important. I'm telling you, they're gonna ask these. Okay, permanent magnets. Okay, permanent magnets keep all their magnetic properties for a long time unless subjected to one of the following. There are three things that may demagnetize a magnet: mechanical shock, such as breaking it or hitting it hardly; strong heating, okay, that's self-explanatory; and proximity to other stronger magnets. So if you put a magnet beside a very strong magnet, it might demagnetize. Permanent magnets are made of steel or magnetic ceramics. Steel is an alloy of iron. Okay, so ferromagnetic materials هني cobalt, nickel, steel, and ceramics. The permanent ones هني steel ceramics. Okay, know these. Permanent magnets are made of steel, whatever. All magnets have two poles, north and south. There are four types: the bar, horseshoe, flat, ring. And these are very, very self-explanatory. Okay, this table, I'm going to come back to it in a second. If a magnet is broken, it forms two new magnets, such that a magnet can be visualized as many north-south poles beside each other. So let's say عندك big magnet on north, south. تكسره into two small pieces. It's gonna be like this: north, south, north, south. Break them into now four pieces. It's gonna be again north, south, north, south, north, south, north, south. You get what I'm trying to say? So even if you break a magnet into pieces, they will still exhibit magnetic properties. Okay, magnets always have a neutral point in the middle. Okay, this is extremely important. Magnetic induction. You should know that magnets can turn other objects into magnets. Okay, if you place a magnet near iron, after that, the iron will have magnetic properties. This is where soft and hard magnets come into play. Soft magnets, they lose their magnetism after the magnet is removed. Hard magnets, they don't lose it, so used to make permanent magnets. So let me go back to the page up here. Hard magnets are always difficult to magnetize, but once you magnetize them, they're very, very hard to demagnetize. Soft magnets are very easy to magnetize, such as soft iron, but since they're easy to magnetize, it's also very easy to demagnetize it, so they're temporary magnets. Hard magnets are used in permanent magnets and compasses. Hard magnets are like hard steel and ceramics, usually steel. Steel, if you see steel, pick steel. But the thing with hard magnets is that they're permanent. Okay. Magnetic fields. This is important. Magnetic fields is the space around any pole. Any space around a pole has a property called a magnetic field, which exerts a force in any magnet placed in that region. It's a vector quantity denoted by B. and its strength is the measure of the force on the particular pole. So the strength of the magnetic field is the measure of the force on the pole. Okay, this is very important. These three. Okay, it's denoted by B. Its measure, the strength is the measure of the force on the pole, and the direction of the magnetic field at any point is actually the direction of the force it produces on a north pole at that point. These are grid questions, and they were in my prep list, so I can almost tell you that yani, they're pretty much gonna come in your exam. Okay, these four. Okay, it's a vector quantity denoted by B. Its strength is the measure of the force on a pole. What is the direction? The direction of the magnetic field at a certain point, or is the direction of the force it produces on a north pole at that point. So it's the force it produces on the north pole. What is the direction? From where to where? It goes from south to north. Okay, this هيدي الحالة, this one here, it was a prep list question I got in my prep list. The blank was north. Okay, so it's the force that it produces on a north pole, but its direction is from south to north. Okay, if you see here, as they shoot, no, whoa, north to south. I don't know why I wrote that. Shit. Okay, so it's always north to south with the magnetic field. I don't know. I fixed it. I uploaded the new notes, updated notes. I changed it to north to south. Okay, so it's north to south. Magnetic fields can be added as vectors, like in compass. Okay, whatever. Plotting compass. It's a small magnetized needle mounted on an axis that rotates freely on. It normally points north. You guys know what a compass is. You have this, find like a needle. It points north. So like if oh no, like they don't have the direction. Sorry, it's always like pointing north. Oh, again, I don't know why I wrote that. Okay, so like if you're like facing this way, and you're standing this way, the compass would be facing up. It always faces the north direction. Okay. Anyway, so like the one used in Minecraft, like is the one. It doesn't have directions, but I'm sure any. Most of you here have played Minecraft. I don't know if you actually used to use the compass. I know I used to, but anyway. Uh, what is it used for? These are very important. What is a plotting compass used for? It's used to identify the poles of the magnet, know which one's north, which one's south. It's used to show the direction of the magnetic north of Earth, right? Earth, where's the north of Earth? It's showing the direction of the magnetic field, of course, and plotting field lines. Okay, please memorize these four. Identifying the poles of the magnet, identifying the magnetic north of Earth, showing the direction of the magnetic field, any magnetic field to find out what's direction, and finally to plot field lines. Okay, you should know these properties as well. The needle is usually a weak magnet of steel. It may be ruined if brought near a strong magnet. If the south pole is brought near a strong north, no damage is done. Yeah, okay. But if you get north near a strong north, it's gonna go 180 degrees. So the north of the needle turns into south. I'm pretty sure, guys, you've seen movies like those adventure movies. They'd be like, oh, like they'd be like, oh, it should be right here, and then they like reach the place, and then there's like nothing, and then they found out that like they had a magnet beside it. Uh, if anybody's seen Stranger Things, I think in the first season or second season, first season, it was in the first season where like they were going somewhere following a magnet. But I think 11 had like a magnet in her pocket for like when they reached the place there was nothing because the magnet in her pocket was affecting the magnet on the needle of the compass. Okay, I'm just trying to help explain all that, guys. Okay, now field lines. Okay, you should know that field lines are smooth imaginary lines. You should know they never intersect. Okay, since a compass can't point in two directions, obviously. Every field line is a smooth curve starting at north, ending at south, like we usually said that the magnetic field is going from north to south. Uh, every field line starts at north, ends at south. They are similar to flowing water, so they are called lines of flux. Okay, these are important. So sometimes you might ask, what are the properties of lines of flux? They're basically asking, what are the properties of field lines? Okay, the lines of for field, I think, are useful to show the direction and to show the strength. This is a CA question 100%. Okay, It's used to show direction of the field and used to show the strength of the field. How do you know when they are strong? When they are brought closer together. Okay, it's important to know that these lines of field, they're drawn tangent to a plotting compass. Okay, this is a question. How are they drawn? They're drawn tangent. Okay, to plot magnetic fields, you use iron filings because when you sprinkle the iron, they will arrange themselves and draw lines called flux patterns. Okay, the iron filings, they show the line of action as curved lines, but they don't show the sense of magnetism. They don't show as if it's going from north to south. Uh, and the second point is that where the iron fillings are close together, obviously there's stronger magnetism. And if they're not close, then they're not strong. So this is north to south. This is how a typical magnetic field uh, going like this. You get it. Okay, horseshoe magnet. Basically, horseshoe magnets, we have north, south, and goes like this. How the patterns are like arranged, it's parallel near the middle, it goes up. Okay, you need to know this. When they ask you when are they parallel, it's in a horseshoe magnet. Okay, NSSN. Okay, this is another one. This is bar magnet. Okay, you should know this. There's a neutral. There's a neutral point in the middle. Okay, this is where there's no magnetic field. Okay. You should know what magnetic shielding is. Magnetic shielding basically uses it to preserve a magnet. You may use a piece of iron to transfer and divert the field to where we want it. So basically, يعني انت if you want, like look, عندك المagnet هون، عندك another magnet هون. So والfield هيك, okay, whatever. Okay, يعني action was like I drew it up here. صح? Okay. Okay. Anyway, so you have this magnetic field, صح? If you get an iron point near it, basically that iron is going to attract some of the magnetic field. So like if you put it here, it's going to be diverted to go through this iron over here. You get what I mean? Okay. To prevent electronics from being damaged by electromagnetic forces, they must be shielded. Like this is very important. The shielding is very important. So basically, this shielding, if you didn't have shielding, all your electronics won't work. They have inside the circuits, they have like iron and stuff on it to prevent it from being damaged by magnets. Okay. Okay, magnetic field in the current meter. What's this? Is this required? It's up until storing. Okay, yeah, let's do this. Place a soft iron cylinder in the gap between the two armatures. Okay. The field line will be directed out of the north towards the south. It's called a plane symmetric field. Such field can exert sideways and just pressure. Okay. Okay, yeah. Basically, if you have north-south, okay, what they do is they put two armatures and they put soft iron in between. Okay, what the soft iron does, like I told you here, if you put iron, it's gonna force the magnets to go through the iron. Okay, so see what it does? It forces the magnetic field to go through this soft iron cylinder from north to south. So it won't go around it, it will go through it. Okay, so the field lines will be directed out of the north, radially yani straight, into the iron cylinder towards the south pole. It is called a plane symmetric field. Such field can exert a sideways tangential push on a current carrying wire placed in the annular gap. Okay, this is just memorized. We should know it should exert a sideways tangential push. I think this is a question as well. Okay. A speaker, loudspeaker magnetic field. Radial magnetic field that is also called actually symmetric radial field. So it's not plane symmetric, it's called actually symmetric. Okay. This is very important here. Okay. A loudspeaker and current meter. This is current meter horn. This is loudspeaker. Loudspeaker, the movement is inwards and outwards. There's no couple created and it's directed radially inwards everywhere. Okay, it's radially inwards everywhere. Memorize this. Okay. Current meter, there's a couple created, right? The cylinder turns. It actually turns. Okay. Radially out of cylinder to south. It goes radially out into the south. It's out of north radially to cylinder. So these two are linked to each other. Okay. Memorize these. Okay. So to explain these just a bit more. Okay, the movement, the magnetic field of a loudspeaker, it moves in and out. Okay, but its direction is inwards. Okay, that's how you do it. There's no couple created, meaning when I say couple means any couple of forces. So let's say you have this, okay, and you move it here or here, so it will turn this because you have a force pushing left, one force pushing it right, so it's gonna turn around. Okay, that's what I mean by couple. So there's no couple in the loudspeaker and there's no movement. But in the current meter, there is a couple. This is a sphere, by the way. So that means هيكون في هيك هيكون في هيك. Okay, because there's going to be action reaction. So it's going to cause the cylinder to actually move. Okay, you should memorize this. And it goes radially out of the cylinder to south. That's the direction. So out of north to the cylinder where it goes to south. Okay, memorize this. هلا الquiz, we'll do it fast. Okay. This we have a plotting compass placed near a magnet at point A. The term magnetic field, what is described? Obviously, the space around the magnet. If the plotting compass at point A points rightwards, the direction of the magnetic field at A is rightwards, obviously, right? The compass points in the direction of the magnetic field. Here, akid, we have repulsion between the two magnets, huh? Not between the north and the south. We're saying this is magnet 1, this is magnet 1, this is magnet 2. Okay, south with south, north with north, obviously repulse. And these two will attract, guys. I'm not going to explain this. خلاص. Opposite attract, like repel. Okay, when a magnet attracts an object made of ferromagnetic material, that object behaves like a magnet. What is called magnetic induction? Remember, when you have an object like iron, ferromagnetic material like steel, iron, cobalt, nickel, or ceramic, if you place a magnet near it, they will exhibit magnetic properties for a short amount of time. This is called magnetic induction. Consider a permanent magnet and 4 points A, B, C, and D around it. A, B, C, and D around it. The magnetic field at point A is directed where? You know, magnetic field, guys, goes from north to south, right? At A, you want to go down to south, so left. At B, it has to go left to south. Wait. Oh, wait, I think they want, they بدهم, okay. So عندك هيك. Okay, so it goes like this, and like this. Okay. And then this one here goes like this, like this. Okay, guys, since my drawing is failing, let me show you the drawing here. So basically, here it's in the equation, it's flipped, but on the edge of the north, it just goes out. On the edge of the south, it goes towards the south, and then it's pretty self-explanatory. If it's north, it goes like this. Okay, and north, but also if it's under, it goes like this. Uh, okay, it's pretty chill. Okay, so B, it's just gonna go out, remember, and D is just gonna go like this to the right. So B and D will both go right. A will go left, صح? And C will also go left. Okay. Uh, question 5. Okay. This again, like I told you, is very important to memorize. This is the table I had in my book. It's difficult to magnetize. أكيد hard. Soft iron. أكيد soft. Used in permanent magnets. أكيد hard. Hard steel. Hard. Easy to magnetize. Soft. Okay, select the rods that can be magnetized by striking them with a magnet. Only ferromagnetic materials, right? Did you say glass and wood are ferromagnetic? No, we said nickel, cobalt, steel, ceramics, nickel. These are all the ferromagnetic materials. I can go back up to here. Cobalt, nickel, steel, and ceramics. Question 7. In the near space around a magnet, a force can be exerted on any magnet. This is called a magnetic field, right? Question 8. A plotting compass is placed along the field line. What type of line is drawn between the compass needle and the magnetic field curve? We said always tangent lines are drawn between the magnetic field lines and the compass needle. Always. The iron filings show what? The line of action of the field lines as curved lines, right? Curved lines need the lines of action, but they do not show the actual sense, right? They don't show the sense. Sense as in the direction, right? Question 10. Iron filings are sprinkled next to a bar magnet. Where the iron filings are packed close together, it is strong, and where they're further, it's weak. Until now, guys, all these questions very self-explanatory. Which shows the correct flux pattern of a single bar magnet? Let's see. Why is this one wrong? Does it go south to north? No. Does it go north to south? But these ones, wait. Yeah, does it go out of the south? No, it doesn't, right? We always know it goes the south side, it goes towards it, right? So that's wrong. Does it go south to north? Obviously. So yeah, this one 3 is wrong because it's going south to north. We don't want that. This one's going north to south, and the south side is going towards the south. We need that. That's important. But the north side is always going out of the north. We don't care about that. Okay. This one was in my prep list, so I think they will get it. Or something where you have to choose a correct magnetic field. Okay. Consider two magnets placed next to each other as shown in the diagram below. Rank the magnitude of the magnetic field at different points around these magnets. Label the point where the magnetic field is the strongest. Okay. Obviously, uh, yeah. A is the weakest because people put D as the weakest, but that's wrong. A is the weakest because it's the neutral point. Let me draw it so you can kind of see what I'm talking about. North to south. Heck. Okay. وهاي. هيك. وهيك. هيك. شو كمان اكتب؟ هيك. Okay. So basically, this point in the middle is the neutral point because nothing passes through it, right? هاي هيك. هاي هيك. Okay. So when you have two magnets like this, the point in the middle is the neutral point where no magnet field passes through it. Okay. بعدين D is the weakest, obviously. Then which one's stronger? B or C? I guess B would be. Why is B strongest? Because yeah, I think because it's closer to north. It's because yeah. Because I think it just has because it passes through the line, the field line. But the north one here it goes هيك. This one goes out, curves. Okay, yeah, I guess it's just B because it makes sense, يا it makes sense. No, it passes through it هيك وهي بتطلع هيك, so it's curved, so it's like weaker. Honestly, I'm making it up, but like I guess that makes sense. والله. Okay, so B is the strongest because it's going out. Or you could just say the pull is greater at the north because like a magnetic field goes from north to south. So B is just closer to north. Credits to Late Alauni. He gave me that answer. Radial fields are fields which weaken away from the center and which remain uniform at a constant radius from the center. Select a magnet arrangement that produces an actually symmetric radial field. Okay, you should remember that the actually symmetric radial field, okay, it's the one that just memorize this, okay? Honestly, you want my honest opinion? Knowing the physics regional, what he's gonna ask is gonna be the plane. It's called plane symmetric. The other one. This one. Yeah, they're gonna ask plane symmetric. Okay. Honestly, that's what I feel. Okay. But know this. Of course, know this. Actually, symmetric is the one for the loudspeaker. Okay, this one it gets weaker away from the center. So أكيد what they mean by weakens away from the center يعني it gets يعني يا أخي just memorize this, okay? If it was plane symmetric it would be this one, okay? Because you could fit هيدا inside it, okay? And actually symmetric are used in what? Loudspeakers. Okay, anyway, moving on. Just before I continue, please make sure you know the plane symmetric one. It would be this one, and plane symmetric would be used in current meters. Okay. Question 14. Okay. You have poles of magnets here, labeled 1, 2, 3, 4. It's the magnetic field. What is X? أكيد it's a north pole because it's going out of it, so it's a north pole. Any plotting compass placed at point what will remain in its orientation. Remaining in an orientation means it doesn't fall under a magnetic field. And where is that? Only in the neutral points. So, point 3. This is the magnetic field of a bar magnet. If a freely suspended small magnet is placed at point 1, it will orient itself in what direction? Obviously tangent to a field line. It will always tangent. It's always tangent, okay? The point 2 in the magnet is its south pole. Obviously, you're going north to south. Question 16. Which of the following are true about magnetic field lines? They're imaginary smooth lines. They never cross. Do they always end at infinity? They never end. They're imaginary lines along which the magnetic field vector points at any point. Every line starts at the magnet south. No, right? Starts at the north. Okay. A small iron needle used to determine direction of the magnetic field is called plotting compass, right? Another way to say that the magnetic fields are as vectors is to say the magnetic fields obey the principle of superposition. This is very important. I didn't write it in my notes, but I remember reading it in the book. Obeying the principle of superposition means that they can be added as vectors. The principle of superposition states that any vector can be resolved into an x and y component and then be added to obtain a net vector or net force or whatever, net magnetic field. There was a question. I don't know if I'll see at the end of the quiz and I'll tell you. The direction of the magnetic field at a point is the direction of the force it produces on a north pole. Again, this was a prep list question, and they asked me to fill in north pole. Okay, please make sure you know that. Okay. Drag and drop the correct answers. The magnet has been split into parts. Obviously, south will be here, or the north will be here. Guys, makes very complete sense. They didn't ask you to fill the neutral. If they put another box here in between the two magnets, it would be neutral. Okay. Question 19. Okay. Two fields suspended magnets are placed side by side. The magnets attract. Drag and drop. What happens? Actually, if they attract any south, north, south. You guys, this is what is. What thought I was so silly. Okay. The poles of a ring magnet are located on its flat sides. So I think this is the ring magnet. In 3D, it would be something like. Whoa, that's a very bad drawing. Imagine this is like a ring, okay? So it will be on the flat side. So this like side here. You get me? The poles of a horseshoe magnet are located on its free ends. Yeah, the horseshoe is like this, like a U. Its free ends are here. All right, so this is where the poles are. To show you the ring better, I just remembered it now. You have this is the north, this is the south. You see what I mean? So it's not on the inside. It's not this. No, it's this. Okay. Question 21. Which of the following describing magnetism are true? The magnetic properties of permanent magnets can be lost through strong heating. Right? That's correct, right? We said it can be demagnetized through strong heating. Magnetic forces are action at a distance. This is very important. They're not contact, they're action at a distance. They're not contact forces. Magnetic forces are interrelated with electric forces, but not gravitation. We don't care about gravitation, but they're related to electric forces to form electromagnetic force. All ceramics are ferromagnetic. No, right? Permanent magnets retain their magnetic properties indefinitely. Do they retain it? No. Question 2. Which of the following materials are magnetic? Cobalt and iron. Kid, we don't care about carbon, aluminum, or silver. It was cobalt, nickel, steel, and ceramics. The question I was talking about was I solved it on my book. Somewhere here. Okay. I don't know where it is, but basically you needed they said something like this, like they said that magnetic field was 8 to the east to north, and then the other magnetic field was 3 east, 5 north, and then they said determine the strength and direction of the magnetic field. What you would have to do is obviously add up the x components. 8 plus 3 is 11. 2 plus 3 is 5, so it's 11i plus 5j. Find the magnitude of it. 11 squared plus 5 squared, whatever, you get something. And the direction is basically they're asking to find the angle theta. It's obviously inverse tan of 5 over 11, right? And you get something. Okay, this is just an example of a question. I don't know how I got 5. 2 plus 5 is not 5. Am I drunk? ما بعرف. Hi 7. Okay, so you get the point. This is to show you that magnetic fields can be added as vectors. Thank you so much for watching and good luck.